Shopify runs 10,000 transactions a second on Postgres. Readers and writers never block each other, not once. Here's the secret. Postgres never overwrites a row, it prints a new one. Think of a kitchen order spike where old tickets stay pinned, just marked voided. That spike is called MVCC. Before MVCC, databases used locks. Select grabbed a shared lock, update grabbed an exclusive lock. Picture one waiter, one order pad, everyone queues behind whoever is writing. A single checkout could freeze your entire product catalog page. That's how databases used to work. It does not scale. At scale, this is brutal. One long-running report can freeze checkout for thousands of shoppers. Locking guarantees correctness, but it kills throughput. Engineers needed reads and writes running at the same time, safely, without stepping on each other. That is the exact problem MVCC was built to solve. Think of Postgres as a kitchen with a ticket spike. Instead of erasing an order when it changes, the cook prints a new ticket and marks the old one voided by ticket 42. Both tickets stay pinned. Waiters holding an older copy still see the original order. Nobody waits. Here's what nobody tells you. Run select xmin xmax on any row and you'll see hidden columns. Xmin is the ticket that printed this version. Xmax is the ticket that voided it. Update never touches the old row. It writes a brand new tuple and stamps the old one dead. Every transaction gets a ticket number called an XID, always increasing. When it starts, it takes a snapshot. The oldest still open ticket, the next unused ticket, and every in-progress ticket. That snapshot is your personal copy of the order pad, frozen the second you sat down. Watch this. TXNA reads balance equals 100. TXNB updates it to 90 but hasn't committed. TXNA reads again, still 100. Why? B's ticket is still in A's in-progress list. Only after B commits does a new transaction see 90. A's snapshot never changes mid-flight. The visibility rule is a checklist. Was this version's creator committed before my snapshot started? Then I see it. Is the creator still running, or did it commit after I started? Then it's invisible to me. That's how every reader gets a private, consistent view. Postgres offers isolation levels that change how often your snapshot refreshes. Read committed takes a new snapshot every statement. You might see different data twice in one transaction. Repeatable read freezes one snapshot for the whole transaction. Sounds safer, but it hides a nasty bug. 2 doctors are on call. Policy, at least one must stay on call always. Dr. A checks, 2 on call, safe to leave. Dr. B checks at the same moment, 2 on call, also safe, both commit. Now 0 doctors are on call, nobody violated a lock, they never touched the same row. This is write skew, the classic MVCC anomaly. Snapshot isolation guarantees each transaction sees a consistent world. It never promised 2 consistent worlds combined stay consistent. Both doctors read truth, both wrote correctly. Together they broke the rule. Interviewers love asking about this exact scenario. There are 2 fixes. First, select for update, which locks the rows you read so nobody else can write them. Second, bump the isolation level to serializable. Postgres then tracks who read what and who wrote what and aborts one transaction before the damage happens. SSI, Serializable Snapshot Isolation, watches for a cycle. Transaction A reads data B is about to write. Transaction B reads data A is about to write. Neither order works. Postgres detects that loop and throws an error. Your app just retries. Correctness without manual locks. Remember those voided tickets on the spike? Postgres keeps them too, for any reader who might still need them. Update a 1,000,000-row table 100 times and you've got 100 million dead tuples lying around. Disk bloats. Scans slow down. Someone has to clean the spike. Vacuum is the janitor. It scans every page and asks, is this dead tuple older than every active transaction? If yes, nobody can possibly need it. Reclaim the space. Autovacuum runs this automatically once dead tuples cross 20% of the table. Skip it and your table only grows. Here's the scary part. XIDs are 32-bit integers. After roughly 2 billion transactions, they wrap around. Without vacuum freezing old rows first, wraparound makes your table's data look like it's from the future. Invisible to every query. Production outages have happened from ignoring this exact number. Shopify runs millions of orders a day on Postgres. A shopper browsing the catalog, a giant select across millions of products, never blocks a concurrent checkout update on inventory. That's MVCC in production. Readers and writers, running side by side, never touching the same lock. Shopify's DBAs watch PG-stat activity for transactions open more than 5 minutes. Why? Every open transaction holds back vacuum. Old tuple versions can't be reclaimed while any snapshot might still need them. One forgotten long transaction and dead tuples pile up fast. CockroachDB takes this idea global. Instead of one XID counter, it uses a hybrid logical clock timestamp across every node. A transaction reading at timestamp t sees any committed write on any node with a commit time at or before t. Same ticket spike idea, distributed across a planet. Zoom out and the whole story is one trade. Locking guarantees correctness by making everyone wait their turn. MVCC guarantees correctness by giving everyone their own copy of the ticket spike. Same correctness. Wildly different throughput, which is why every serious database now uses some version of MVCC. In your next interview, say exactly this. Postgres uses MVCC. Every row keeps xmin and xmax so readers see a consistent snapshot without blocking writers. Then drop write Skew as the follow-up gotcha and SSI as the fix. That sentence separates junior from senior in this answer. This isn't new tech. Oracle pioneered MVCC in the 80s. Postgres built it in from day one in 1996. Serializable Snapshot Isolation landed in Postgres 9.1, giving you full correctness without full locking. Decades of research compressed into a feature you'll use in your very first CRUD app. This also explains that confusing bug report, I used a transaction but got stale data. Under repeatable read, that's not a bug, that's the point. Your snapshot froze at transaction start. If you wanted fresh data, you needed read committed or a brand new transaction. The proof is in production. Shopify, GitHub, and Stripe all push over 10,000 transactions per second through Postgres. Millions of orders, Git pushes, and payments, with zero reader-writer blocking. That number only exists because of the ticket spike sitting quietly underneath every query. And it's not just Postgres. MySQL's InnoDB does the same thing with undo logs instead of tuple copies. Amazon Aurora rebuilt its storage layer around MVCC principles. CockroachDB distributes it globally. Different engines, same idea. Never overwrite, always version, let readers freeze their own snapshot. So next time someone asks how Postgres handles concurrency, don't say locks. Say versions. Every write prints a new ticket. Every read carries its own frozen copy of the spike. That single idea is why your checkout and your catalog browse never fight over the same lock. Postgres never locks the spike, it just keeps printing tickets. That's how Shopify, GitHub, and Stripe run millions of transactions without readers and writers ever colliding. Subscribe for the next episode. What happens when the spike itself runs out of room? See you there.